Hello, my name is Joshua Rasera, and I am a third-year PhD student in the Space and Terrestrial Resources group at Imperial College London. Today I will be speaking to you about how the development of technologies for utilizing resources in space will contribute to both sustainable space exploration as well as sustainable terrestrial mining practices. Space Resource Utilization, or SRU for short, refers to the exploration, planning, mineral processing, metallurgical processing, and sale of resources in space. SRU has been a point of interest and study for the space community for approximately 60 years. However, it has only been within the past few years that SRU has begun to transition from an idea to reality. Let's now explore what materials of interest are available to the prospective space miner. Looking specifically at the context of the Moon, there is a large array of materials that could potentially be exploited, including base metals such as iron, magnesium, aluminium, calcium, and silicon, all useful for in-situ manufacturing and construction. Thorium and uranium are useful for large-scale power systems, as well as rare earth elements, potassium and phosphorus, necessary for the semiconductor industry. Titanium is available for the manufacturing of strong, lightweight aerospace components, as well as for construction. Volatile materials implanted by the solar wind, such as hydrogen and oxygen, are useful for power generation, energy storage, and fuel. And last, potentially billions of tons of water, useful for producing rocket fuel, sustaining astronauts via life support, energy storage, hydroponic farming, and more. As of 2016, the United Launch Alliance in the United States confirmed that they would be willing to pay up to $3,000 per kilogram of fuel, namely oxygen, hydrogen, or both, made available to them in low Earth orbit, or up to $500 per kilogram on the surface of the Moon. This announcement was quite historic, as it was the first time in human history that a standing order has been placed for a commodity produced somewhere other than on Earth. The first target for SRU is to produce fuel in space. This can be accomplished through the extraction and electrolysis of water ice at the poles, or through the electrochemical reduction of oxygen-bearing minerals. To quantify the financial benefit of SRU, a recent report produced by the Government of Luxembourg and PwC found that space resources could realize market revenues of up to $190 billion, as well as produce efficiency gains and spillover revenues, each worth up to $150 billion by 2045. This tracks well with predictions about the overall growth of the space sector made by Bank of America Merrill Lynch and Morgan Stanley, both of whom predict the space sector as a whole will be worth over $1 trillion by 2040. We have now established that the Moon is an ideal destination for SRU, so I would like to move on to discuss the work that our research group at Imperial is doing to help make SRU into a reality. Here you can see the lunar mining flowsheet that was developed by the European Space Agency's SRU topical team, led by my supervisor, Dr. Catherine Hadler. As with a typical terrestrial mining operation, we have three broad stages. Excavation and haulage, whereby our run-of-moon material is initially collected. Beneficiation, where the as-mined material is crushed, sized, and enriched. And extraction, where we are able to produce the desired end products, such as pure and alloyed metals, oxygen, fuel, and other volatiles. Our group is focused on the beneficiation stage, specifically on the sizing and enrichment steps. Why do we need to beneficiate? Well, much as on Earth, naturally occurring homogeneous deposits of desirable minerals, pre-sized, sorted, and ready to go, are not available on the surface of the Moon. Furthermore, not all of the minerals that are present are equally suited to oxygen production. One material that is of particular interest to SRU is an iron-titanium oxygen-bearing mineral known as ilmenite that is found in the dark gray Mare regions on the Moon. Ilmenite is attractive for early SRU operations as it can be reduced with hydrogen at relatively low temperatures. Some hydrogen reduction systems, however, require ilmenite concentrations in excess of 80% by mass and for the feed to be sized optimally. Clearly, such a feed would not exist naturally on the surface of the Moon. Hence, a beneficiation process would be necessary to produce it. Furthermore, beneficiation must be considered in order to maximize confidence in an SRU operation's ability to meet a given demand. The image on the left shows the relationship between the mining rate and the reduction step feed rate versus the grade of ilmenite contained within the regolith. The mining rate increases linearly, while the reduction step feed rate decreases linearly, since the oxygen yield is correlated to the ilmenite content. What this implies is that reducing the reduction step feed rate by increasing the content of ilmenite will result in an overall increase in the mine rate. We then considered a theoretical lunar mine with an annual demand of 1,000 kilograms of oxygen. A statistical estimation of the confidence levels in the mining and reduction feed rates required to meet this demand was performed using a Monte Carlo simulation, the results of which are found on the right. The parameters varied in the simulation were particle size, agglutinate decontamination, operational availability, and oxygen yield. After running the simulation 10,000 times, my supervisor, Professor Jan Silliers, found that it was a mining rate in excess of 60 kilograms per hour that would be required in order to have 90% confidence of meeting the annual target. This rate is 10 times higher than the estimates made previously that did not consider the regolith variability or beneficiation steps. Clearly, beneficiation must be addressed in future SRU operations. So what are we doing about this? Well, our research group has two main focus areas. The first is on the development of dry beneficiation technologies for use on the lunar surface. Dry methods are necessary for use on the moon due to environmental constraints and a lack of flowing water. Here you can see the experimental rig that I designed and built. It employs a process known as triboelectrification, whereby individual mineral particles gain either positive or negative charge through repeated contacts with surfaces or other particles. The magnitude and polarity of the acquired charge is a mineral-dependent surface property that is then used to perform separations by mineral type, using strong electrostatic fields. The plots that you see on the right show some of the results from my initial single material characterization tests. Here I used a simple vibrating copper pipe as a simple tribocharger and 5 different electrostatic field strengths to characterize the charging and freefall motion of ballotini and crushed ilmenite. These initial tests found that the particles did acquire sufficient charge to have their motion affected by the electrostatic field. However, the tribocharger itself requires further optimization in order to increase the proportion of particles that acquire sufficient, meaningful charge to be affected by the electrostatic fields. The second focus that our group has is understanding the underlying physics that governs the tribocharging process. While tribocharging itself has been known and observed for thousands of years, the actual mechanism that drives it is poorly understood. This work is a focus area of my fellow PhD student and co-author, Ruben Cruz. The image on the left shows the temperature and humidity-controlled glove box used to perform saturation charging experiments. The plot on the right shows how the specific charge of PTFE, PVC, and LDPE particles vary with respect to particle radii. While larger particles acquire greater absolute charge than smaller ones, the charge per kilogram of smaller particles is appreciably higher. This result has a direct impact on my own research, as it indicates that smaller, lower mass particles should interact more strongly with an electrostatic field relative to larger, more massive ones, thus improving separation characteristics. Many of you may be wondering how our research can be beneficial for terrestrial mining operations. Well, traditional wet mineral processing methods, such as froth flotation, are highly efficient, but they are very expensive to deploy, especially in water-risk areas like the Australian outback or sub-Saharan Africa. Since we cannot consider wet methods for use on the moon, we are forced to develop and mature effective, reliable, and resilient dry methods for a demanding and remote environment. By proving these technologies in space, it will hopefully help to build confidence on the part of the terrestrial mining sector to consider replacing wet mineral processing techniques with dry ones. This shift could potentially save hundreds of millions of tons of fresh water each year, as it will also help to reduce mine capex, opex, and impact on the environment. In conclusion, space resource utilization is coming and will likely be demonstrated by the end of this decade on the moon. SRU will be critical for the establishment of a permanent human presence on the lunar surface, as well as for establishing and enabling longer duration human spaceflight missions to more distant targets such as Mars. Furthermore, the subsequent SRU economy that emerges will offer traditionally terrestrial industries the opportunity to break out beyond the silo of Earth. Beneficiation will be an integral part of the SRU flowsheet. Given the restrictions imposed by the lunar environment, reliable and effective dry beneficiation systems will be developed and matured out of necessity. Triboelectrification and freefall separation have shown promise for this application. However, there is still work to be done to understand the underlying mechanisms and to optimize the charging process itself. Finally, once these techniques have been demonstrated on the moon, spin-offs will offer terrestrial miners an effective enrichment method, both with lower operational costs and environmental impact. If you are interested in further reading, you can find the resources mentioned throughout this presentation here. And with that, I'd like to thank you for your attention, as well as to thank Imperial College, the Luxembourg National Research Fund, the European Space Agency, and the Natural Sciences and Engineering Research Council of Canada for their support of our research. Thank you again.